Maksym Titov got this laptop. I just tell you what about it. So of course he is not as senior as Daniel, but he is working like and at present, he
whatever you need.
Zoom. Oh, and he's my
Zoom
application. Just try. But the main thing is that you work mainly many different experiments, but the recent time his main focus is this gaseous detector. And San has a dedicated group which is called the RT50 watt system, who is mainly looking for the gaseous detector for the future generations. For the dual chamber or big detector, we cannot use the single detector because of the so big detector. But this specific technology, as Daniel mentioned, that specific gas detector is not faster environment. So this is the new technology.
It's a French keyboard.
Gas detector, what is called the multiple.
No, do it. No, it's okay.
He is the one of the main partners to build that effort. And also, actually, he is the looking for, he is also a founding member of a conference series called TIFR, which is mainly trying to propagate the knowledge in the high-energy physics to the other fields in the medical or the other application. And as I said, he is the founding member and he is now the chair of that advisory committee of the field. So I think he's the right person to talk about the future gaseous detector, and requested him to give the lectures and PhD for it. So thanks, Maksym.
Thank you. Thank you very much, Govinda, for this introduction. It is, I don't know, can you hear me? Okay, because I cannot hear you. Okay, good. Okay, thank you very much for introducing, and it's a pleasure to be here and a pleasure to see so many young faces. It is always good. And we are certainly sure to support your interest and probably to tell you more exciting things which can probably help you to more engage with science. And before I actually really start, I would like to ask you, who from you had some lectures on gaseous detectors before? Okay. Don't be shy. Yes, Daniel, sure. Thank you. You will help me to translate. So I see, and I assume that none of us was working really with a gaseous detector before, right? So it is, yeah, okay. So, but the lectures on instrumentation in general, some of you, I can imagine, have heard before, right? In the universities. Okay, very good. So then I will try to introduce you to the field of gaseous detectors. And actually, thank you. Let me check. Works. No, it doesn't work.
No, it's not giving some.
But I need somehow to.
It's not working.
No, I click and it doesn't work. I don't know why.
They have French language, sir. They have said French language.
Yes, it is a French keyword. No, but I don't understand why this one doesn't work. Ah, you didn't put it about this one?
Yes.
It is here.
Yeah, no.
Okay, very good. Okay. So some technical issues, okay. Okay, very good. And I profit a lot from the introduction of Daniel because he gave already and exposed you some of the topics which we will be discussing today and tomorrow. And as Govinda mentioned, what we will be discussing today is some sort of tour or introduction from the very basic ideas to rather complex gaseous detector systems, which you can see built at the Large Hadron Colliders and not only. And of course, we start the tour from the beginnings of the gaseous detector and actually the particle detector, as Daniel explained you, from the multivia proportional chamber, drift chamber, going to the time projection chamber and going to the more novel concepts of the micropattern gaseous detector. So this is what we are supposed to go through, of course, also learning about the basics, physics of the gaseous detector, because there is a lot of the many interesting things to learn. Some might be more complicated for you, some less. but I hope you will be able to get a general picture what is gaseous detector and how they function also from the physics point of view. But following up in the line of Daniel, so whenever you come to the LHC and you would like to make a collider in experiments, Daniel was saying you need a theory, first of all, who effectively interacts with experimentalists. You need a cafeteria where theorists and experimentalists meets, as Daniel explained, and gets together what to calculate new physics diagram or precision physics diagram. Then, of course, you need an easy, understandable drawings, which you use to construct something, detector, accelerator, whatever is. And of course, you need a tunnel for accelerator, magnet stuff whenever you install all this type of things. But this is not everything. You also need an access to experiments. Daniel was showing you the cathedrals of the 21st century where everything is built to the micron precision. And actually, you need to be able to access all these detector elements. Then you have the so-called control rooms where the physicist sits 24 hours, 7 days a week when the collider is running and looks at all of the data which coming from the detector is good. And actually, if something is not, then you try to. And of course, at the end of the day, like discovery WZ bosons, you need a Nobel Prize. This is absolutely clear. But we will be discussing this lecture concentrates on detectors. So we will talk about the detectors, particle detectors, and in particular gaseous detector. And here you can see physicists, which is setting up experiment. Okay, good. So if you look in the history of the gaseous detectors, it started from the beginning of the century with the invention of the Geiger counter, which actually was some sort of the first gaseous detector device, which you know is currently still used for measuring the radioactivity levels. And then there was a couple of developments in different, based on the concept gaseous detector. So you have some volume which is filled with gas. How to select the proper gas we will discuss with you. And then there are different geometry. Either you do 2 electrodes as a parallel plate mode, or you do a multi-wire proportional chamber wire surrounded, thin wire of the few tenths microns diameter surrounded by cylindrical cathode. Yeah. And then there was a different modifications of the parallel time projection chamber, resistive plate chamber we will be discussing. And from the beginning of 90s, there is a development of the micro-pattern gas detectors, novel detectors, which overcome in characteristics the wire type structure or parallel plate structure for many applications. So, as I mentioned already, the family of the gaseous detector with glorious tradition starts from the first wire counter, which actually was used by Rutherford in study of the natural radioactivity, and which actually earned him a Nobel Prize in Physics in 2008. This counter was sensitive to alpha particle, yeah? So the first counter, which was sensitive to the single electrons, was a Geiger counter, which was introduced in 1928. And actually, the Walter Bohr got the Nobel Prize in Physics in 1954 for the coincident methods. But this was the first prototype of gaseous detector, which is still being used, but unpractical for many of the collider applications now or many other things, because it requires a very high voltage to operate, and there are some other drawbacks. But of course, the field of gaseous detector and instrumentation in general was revolutionized in 1968 by the development by Georges Charpak, the multi-wire proportional chamber. And here you can see the first prototype chamber where Georges, Fabio Sauli, and engineer Jean-Salut Santiard is building this chamber. And it was really something new. So this was we can say, a first revolution in gaseous detectors and instrumentation in general. Why? Because before the 1968, detecting particles was mainly a manual, tedious, and labor-intensive job. For example, all this bubble chamber, emulsion technique, etc. So somebody had basically do the things manually and select images manually. And of course, this was unsuited for the case of rare particles, which we are searching at collider experiment. Georges Charpak developed the multi-wire proportional chamber. it's actually the major element. It's marks the major transition from the manual to electronics era, because it was combining the image detector such as bubble chamber, emulsion, and logic detector electronics into the electronic image detectors. The key element of the multi-wire proportional chamber was not only that he extended the technology of the gaseous detector to the large area with many parallel wires, but the key element was that each individual wire was connected to the individual electronics channel. This was one of the major breakthroughs. So you get a fully electronics image device, which could be extended to the area of meter squares. So it was a real transition in the way how we started to detect particles at the collider with the invention of multi-wire proportional chamber. We will be discussing about this in details. Now I'm trying to tell you why this field is interesting, to provoke you to follow up the things and to ask me of course questions. So the multi-wire proportional chamber was the first electronics image detectors. And actually, as I mentioned, it was very useful for collider experiment, but also George Sharpak in 1989 found a BS Space company, which was also using multi-wire proportional chamber for the commercial autoradiography and also low dose 3D imaging. If you will go to the website of this company, you will still see, it exists. And you see it basically, this is what you can find on the website. Our digital autoradiography system leverages the gas detection technology invented by our founder, George Sharpak, Nobel Prize in Physics in 1982. So it also shows that all of the detectors about we would be discussing, and you would have a special lectures for collider experiments. They have a lot of the spin-offs in the other domain, medical domain, but not only. And here you can see the George Sharpak with friends in the 70s or 80s, I don't know the picture, and actually the George group, and I wouldn't say it was a prototype, but it was a start of the gas detector development group, which plays a big role also in the development of the micro-pattern gas detector technology, and Leszek Kropelewski, who is the head of this group. He's retiring this year, but you can see, so this picture was taken some years ago. In all cases, so as we discussed, multi-wire proportional chamber, about which we will be talking, played a major role in the UA1, UA2 experiments, what Daniel was telling you about. And actually, it is used as a tracking detectors, the wire or drift chamber in the center collisions. The wire you can see stretched parallel, it is seen as a reflection here. And it's actually can be seen still in the CERN microcosm exhibition. And as was already mentioned by Daniel, it led to the discovery of W and Z bosons, and Carl Ruby and Simon van der Meyer received the Nobel Prize. The first revolution, as I told you, in gaseous detector was a wire chamber. The second revolution, which I can call in gaseous detector, was the invention of the so-called time projection chamber. It is basically the basic idea of this, that you go from 2 dimensions to 3 dimensions. And actually, here you can see at the collision points, you can, for example, build it around the collider, but then you make a very, very big volume with a parallel electric magnetic field, and electrons which is produced here slowly drift over the distance of a few meters to the redoubt electrodes, which can be assembled with multi-wire proportional chamber or micro-pattern gas detectors. And here the image is recorded. The advantage of this is that while electron drifts, it creates an ionization, and you can have a lot of the clusters along the way, which you can collect at the redoubt electrodes. And you can reconstruct not only the position how the particle was traveling, but since you have a lot of the measurements, you can reconstruct also energy resolution, energy deposition, which transfer you to d over dx measurements. And from d over dx measurements, you can try to identify the different particle types. So, and you collect information in space as the arrival time of the electron, but also in time. So you have a 3D tracking. 2D comes from spatial dimension and 1D comes from the time dimension, okay? So this was, and actually first it was proposed for the electron-positron collider FEB4 by Dave Nygren, and more chambers were built, but recently the readout electronics, as I mentioned, can be either multi-wire proportional chamber, or recently the readout electronics of the time projection chamber usually consists from the new generation micropattern gas detectors. And here you can see one of the most modern chamber. You can see the size, which is time projection chamber installed in the ALICE experiment. You can see the size. And as I mentioned recently for the upgrades, the readout, which was consistent, you see it's end plate as we as you see it, but you don't see the readout, you see the cables, electronics, but the readout was replaced, multi-wire proportional chamber were removed and micropattern gas detectors were installed, because the rate capability of the ALICE experiments requires faster devices than what can be done with multi-wire proportional chamber. I hope for the time being everything is clear, right? It should be simple. Or something not clear already. Don't be shy. Okay. So, as I mentioned, gaseous detector, we discussed multi-wire proportional in drift chamber, which were invented by Georges Charpak. This was the first revolution in gaseous detectors. Then the second revolution was the invention of time projection chamber. And then from the beginning of the 90s, the micropattern gas detectors started to play a role. It's actually arrived, we will be discussing about this, because of the possibility modern advancing in photolithography, which actually initiated these developments and allowed to build a much finer distances between anode and cathode, and much finer structure, electrode structure, which you need in case you have a higher rates of particles. So it was really industrial technology, photolithography, which allowed to build. And here you can see the different type of technologies we will be discussing about this were invented during these years. And here it just shows you that that gaseous detector is still and will remain the primary choice for large area coverage for raw material budget, okay? It is used mostly in muon chambers. It is also used in case for TPC, when time projection chamber, when you have a lot of points along the track for D over DX measurement and for particle identification capability. But if you will look for the future colliders, it is still used mostly in the muon systems, not so in tracking, as Daniel was saying, has everything becomes a silicon. But in muon systems, you cannot find other technology where you can precisely measure the coordinate and cover the large area at affordable cost. And here you can see some particular applications for future hadron collider like FCCHH, for future lepton colliders such as linear collider LC, CLIQUA, FCCE, also for the future electron-ion collider, which will be built in Brookhaven in the beginning of the 2030s. So it is still the technology of choice, and it's still quite widely used in different areas. And also, just to say, mention one point, the micropattern gaseous detector, as I mentioned, which appeared around 90. So it's really new developments with the first concept microstrip gas chambers, then developing more robust concepts such as gas electron multiplier, micromesh gaseous structure, another one. So this was a starting point for the developments of the MPGD. And then the RD51 technology-based collaboration has been established at CERN. And it's actually, many things has been started before RD51, as you can see, but it's allowed to consolidate the resources. And as an outcome, for example, there is many experiments and collider experimental HC upgrades, which pick up this technology for future upgrades of the detectors. But not only neutrino physics experiments, electron plus ion collider. And actually, just to mention, this collaboration served for 15 years. From the next year, CERN is planning to make a bigger collaboration in size. And actually, there would be one collaboration for the all gaseous detector technology, including micropattern gas detector and other. And this is actually would be a much larger collaboration, the RD1, the so-called. So there is a future of this technology. And I would like also to mention that with RD51 collaboration, it was a pleasure in 2014. We visited in Kolkata. There was RD51 collaboration meeting organized by our colleagues from the VECC and Saha Institute of Nuclear Physics. And we have a very nice time. And actually, it was a workshop on advanced detector, which not only included MPGD technology, but also RPC technology. You can find some slides and links from this workshop. So it is a pleasure to be in India again after 9 years. And here you can see some article from the Tson Courier in 2015, after the things has started about the developments of micropattern gas detector and the recent progress in them, which is a really, really very rapidly developing field. Okay, just before we go into more technical points, one of the points, the MPGD were recently adopted and installed in 2022 as upgrades to 3 of the 4 major experiments of the LHC. The Micromega, the so-called new small wheel, here you can see, was installed in the Atlas Muon system. Here you can see the size. And so basically, Zali's TPC, time projection chamber, as I already mentioned, replaced multi-wire proportional chamber with gas electron multipliers because of the need of operating at higher ion collision rates. And muon chambers in the CMS experiments has been installed based on the GEM technology. And actually, this successful implementation just shows the maturity and the level of the dissemination within the HEB community and the reliability. So basically, this is important milestones which were achieved actually last year. So why actually the particle detector evolves and why we say we need a change, for example, from the multi-wire proportional chamber to other detectors. Here you can see in a real time a collision in the ALICE experiments, which has a low luminosity crossing rate, but very large particle multiplicity. And here you can see you collide. You collide, and here you can see the number of tracks which appear in every event. And this is what creates a challenge for the detector. So you basically need to reconstruct all these detectors. So here you can see the time which is running within the 10 nanoseconds. So your detector should have a very high granularity, and your detector should have a resolution and very nice also time resolution. And this is what you have to reconstruct based on your collisions in a proton-proton or heavy ion collisions at the Large Hadron Collider. Okay, so I would not go through the slides, but if we discuss about the tracking detector history, as was pointed out, I mean, starting from the nuclear emulsions, cloud chamber, and Geiger counter, the major tool for operation was the bubble chambers, and their peak time was between 1960 and 1985. And after the discovery of the multi-wire proportional chamber, wire chamber, and drift chamber, they were dominating and recently started to be replaced by the micropattern gaseous detector. But since late 80s, the solid-state detectors are in common use. They started as a small-sized vertex detectors at the electron-positron colliders, then reached up to the 200 square meters of the silicon in the CMS tracker. And now for the calorimetry in the CMS experiment, in calorimetry, not for tracking, the total amount of the silicon would be 600 square meters. So you can see they start to dominate everything from the central point. And there are different technologies. Frank Hartman will be later giving you a lecture about this. But of course, close to the interaction point for the fine spatial resolution, and also from the consideration of radiation hardness, the silicon detectors becomes much more common inside. And if you look on the state of the art of the tracking and vertex detector, as I mentioned, there are 3 major technologies. One of them silicon detectors, which is basically based on the production mechanism of the electron hole pairs and the solid state material. Then there is a gaseous detector, wire chamber, time projection chamber, micropattern gas detector, ionization of gas. And then the third option, which is maybe not so common but still used in the LHC upgrades, like in the one of the experiments LHCb, is a fiber tracker. When you detect scintillation lies with a photon detector, which is sensitive to single electrons, for example, the new silicon photomultipliers. And this is a type of the tracking detectors which is currently being used. And this is actually ends some sort of the introduction. Before I go to technical questions, I would like to ask your questions. Questions up to now. Don't be shy. Yes.
Hello, sir. I'm Nikhil. What are the modern materials that could be made for the electrodes in the gaseous detectors?
Sorry?
So what are the modern materials used for making of the electrodes in the gaseous detectors?
Material of electrodes?
Materials.
Materials, okay. So basically for the materials, it is in the wire chamber, you use usually gold-plated wires. Because we will be discussing about this, you need mostly chemical inactive element. We will be discussing this because it can relate it to some polymerization or some fragment of the gases deposited on the wire. So usually it was you were doing some gold-plated wires or sometimes aluminum wires. But in the new design of micropattern gas detectors, you use mostly resistive materials. So in resistive materials, it can be like a diamond-like coating, etc., etc. But of course, you need the metal to which you apply voltage, and then you can, dependent from your. So there is, in the wire chamber area, I would immediately told you, build anode from the gold-plated wire. For the new micropattern gas detector, I won't give you the general rule of thumb.
So
Yes.
I have a question. It is about the time projection chamber. So you measure the Z coordinate using your time.
Yes.
So what is a typical resolution of your timing?
We will be discussing about this. This is more dependent from the electronics and so forth for the drift time. So, I mean, it is, you can measure, it distributes, we will discuss it. It depends from the drift, but you aim for hundreds of nanoseconds, let's phrase it like this one in this case. Because it depends, but the value of the hundreds of nanoseconds would be correct. Yes. But we will be discussing about this more.
Unlike scintillator detectors or other detectors, like wire detectors, you are based on the current flowing in the wire. So there must be a large electronic noise. So how can we suppress like electronic noise from the actual signal?
Well, we will be discussing about this. So basically, you use the so-called concept of gas multiplication, which allows you to multiply original charge and be well above the electronic noise. But you're right, it is different from ionization chamber where you measure currents. In gaseous detector, you can multiply. Yes.
Also, so what are the gases are mostly used in these detectors?
We will discuss. It's usually the combination of noble liquid, noble gas plus some admixture, and I will tell you why we are using. But right, very good question. We use a combination of the gases. Yes.
Yeah, do all the particle deposit its all energy to the cathode or anode?
Yes. The particle deposit energy between anode and cathode, and then the electron drifts towards anode and ions to cathode.
Then it deposit its all energy, or it saves?
This is good question for the introduction. We will continue how it deposits. It deposits the energy based on a beta block formula, d over dx. Of course, the gaseous detector, as Daniel was saying, we try to put minimal materials. This is why, in this way, gaseous detector wins over silicon, because in particular, the time projection chamber, the multiple scattering happens only in gas. So in tracking detector, you want to, that the gaseous detector, that the particle loses minimal possible energy. You try to reconstruct the trajectory without disturbing the particle. And in calorimetry, you want all the energy to be absorbed. This is a different, dependent from different concept. In gaseous detector, you try, this is why gas is preferential, because if it's gas, no engineering, no support structure, then it creates minimal material for multiple scattering. And by this, you measure the track of the particle without disturbing. Okay, so now we go further. So the working principle of gaseous detector, you have a charged particle which is passing through the gas and ionizes, creates electrons. Then these electrons, this is a drift wire which goes perpendicular, and the field is applied to this wire. The cathode is somewhere here, and the electron drifts towards the wire, and around the wire it happens the so-called gas multiplication. So basically, whenever the particle goes, first you need to transport the electron towards the wire and then multiply the next to the wire. And then you record the signal from this wire. This is a typical simulation of the event at the scale of 100 micron to 1 millimeter, which gives you a feeling of this process of ionization. Okay, so for the gaseous detector and for the signal generation, now we come to the more technical questions to discuss. We will discuss about the few important things. As we discussed, first, the particle which is passing through the gas volume need to ionize the gas. Then you need to transport the particles created, electrons which is created towards the anode, and to anode, electrons to anode and ions to cathode. And this is determined by several factors, the so-called diffusion, electron and ion mobility, and drift velocity. This is what we're discussing. Some of the electrons, while they're transported to the anode, can be lost, the so-called attached by the other molecules. And then at the last, you have the process of the charge multiplication or gas multiplication. And you actually, all this would be impossible. You also need a reliable simulation tools in order to address the things and then to measure and then to compare. Okay. The primary ionization statistics. So whenever the particle goes through the gas, it loses the energy through d over dx, energy loss transporting in the gases. I'm sure that you should learn in the lectures particle interaction with matter, right? So there is a Bethe-Bloch formula which gives you. So basically, the particle going through the medium gas creates your electron-ion pairs. But some of these electrons can have a sufficient energy in order to create the so-called delta electron. So the electron has a sufficient energy to continue ionizing the gas, yeah? So this is what we will call the primary number of the ionization clusters. And this is what we call the secondary number of the ionization clusters if some of these primary electrons can produce, for example, few more electrons or even more. So the typical numbers of the electron-ion pairs is 30 primary electron-ion pairs per centimeter. This is very small. Even if you count the total ionization, it would be on average 100 electron-ion pairs, right? You cannot detect it with a standard electronics such a signal. This number is Poisson distributed. And actually, it sets up the limit on the detector efficiency, because if you do a detector very thin, there is a probability that particle will not give you any electron-ion pair. For example, for argon, with 1 millimeter of gas, the efficiency that at least one electron-ion cluster would be there is 92%. Yeah, so you need a thinner detector in order to be able to register more. And the ionization probability, as we discussed, sometimes you have an electron-ion pair, sometimes you create a cluster. And for different gases, the probability to create an electrons is actually following, not as the electrons is not evenly spaced. It's a number of probability as a function of the cluster size, the number of electron-ion pair when the particle passes. And here you can see for different gases, for argon, for neon. So on average, if the particle passes through argon, 66% contains single electron-ion pair, but 34% contain more than one electron-ion pair. And this is what we call cluster. This is what changes your statistics ionization. And what is important to point that those electrons, which is delta electrons, which can further potential ionize the medium, they actually create a problem. They create a problem in the coordinate measurements. Because, for example, 0.6% of the list of electrons, have an energy 1 keV, which is enough for this electron to propagate 70 microns within the gas, okay? So this is why you have this so-called resolution and the long tail, because many delta electrons can propagate a lot, and by this you lose the information about the primary place of the electron-ion interaction. There is another very important point, which is basically comes from the Bethe-Bloch formula. In principle, the Bethe-Bloch formula describes you that any ionization process is a quantum mechanical transitions, which is, initiated by the Coulomb field of the particle and the field created by the neighboring polarizable atoms. And the average energy losses is described by Bethe-Bloch formula with Steinmeier density correction. And what is also important, the fluctuations, you need to take into account the electrons are quasi-free. Okay, because they belong to the different orbit. This is why it is important that in addition to this formula, in order to receive energy deposition correctly, you need to take into account the photoabsorption ionization model, which allows to simulate the energy transfer within the different atoms with the relaxation cascades and simulate the delta electron, because many of the things is not so simple when I explain it on the figures, yeah, because you have a different. And here you can see for this photoabsorption model, there are several different formulas. And this is what leads, in case you really look, for example, for the energy loss deposition of the 2 GeV protons in a 5 centimeter C argon gas, the data will show you that it's different from Landau, because in this way, in the photoabsorption formula, takes correctly from which shell within the atom electrons is ejected, okay? So, but this can be simulated. And this is simulated in some of the programs like HEAT, for example. It takes into account properly of the energy depositions to the outer shell, to the inner shell, and to the things. And then, as I mentioned already, in each gas, you can do statistics, the key elements. So in average, for each gas, you produce on average 100 electron-ion pairs, okay? And then this table also gives you like energy loss, like ionization potential. And for any of the gas mixture, you can actually, from this table, evaluate how many primary and total electron you can give by just simply, for example, if you take 70% of argon, 30% of CO2, by the concentration, you evaluate how many pairs per centimeter you get it. And also for the total one, you take, in this case, the d over dx and divide, in this case, on the energy which is effectively needed to produce electron-ion pairs, okay? But again, as was already the question, we get only 100 electron-ion pairs ionization process. And the typical noise, even of the modern ASICs, before it was 1,000 electrons, but even now, it's 100 electrons is the best things. So you cannot detect the signal of 100 electron-ion pairs. So what do? You actually need to multiply these pairs. And this is what the key element, gas multiplication, comes into the game. But this we will discuss a little bit later. First, as we discussed, we need to, when we produce electron-ion pairs, first you need to move them towards electrons. And this means that the electron ions will collide with the molecule of the gas which you have in your counter. And through this collision, under the influence electric field will drift towards the electrons. So the electron transport theory, it's actually it describes you the balance between the energy acquired from the field and collision losses. So electron goes, it collides with atom, it collides with another atom. Actually, if you will look, what we call the drift velocity, with which average drift velocity electron moves from the point of creation to electrode, it's approximately 100 times smaller than the real electron drift velocity, because it scatters in between the atoms and continuously changes direction, but we cannot measure this velocity, okay? So because it's randomized through the collisions. What we can really move is on average when the electron reaches the cathode. And here comes a very complicated discussion, because it depends strongly from the cross sections of interaction of electron with different gas species. And velocities actually determined by the atomic cross section, the probabilities, for example, and the function of the electron energy, very complicated, okay? So the electron gained a little bit more energy and it has a different probability to collide. Usually you have three gases, 2 or 3 gases, noble gas plus some another admixtures. So basically you need to calculate everything properly. And in addition to this, these cross sections have a very strong dependence on the energy of the electrons. So the closer, for example, it's a field to the wire, the more electron can get the energy between the collisions. So it basically defines on the formula by the cross section. And again, there is a very big difference between noble gases and CH4, because noble gases like argon, they don't have a low energy vibrational and rotational degrees of freedom. You can only excite or ionize noble gas. This is different to the molecules like CH4, CO2, because in case of noble gases, you can have only elastic or inelastic collision. In case of CH4, if electron collides with gases which have a different this type of structure with many molecules, many rotational degrees of freedom, they can lose a little bit of energy. You see, so this is a big difference between. And actually, this is one of the points which we was just saying. You see, for the cross section of argon, you have the cross section which basically have only elastic components until you start to excite or until you start to ionize. This is the energy of about 10 electron volts. You see, and for CO2, for example, you have a lot of vibrational modes before 10 electron volts. This is this area in this domain. So this is where actually electron a little bit heats up by the electron's electric field. It gives back energy to CO2, part of the energy. In case of argon, it just can randomly, without changing the energy, change the direction. And actually, this is well simulated by the program. Again, there is a lot of the simulation tools, MacBalls, which has a big number of cross-section for many, many molecules, for the many noble gases. So this is what you actually use, because again, you need a microscopic tracking. You cannot really concentrate. What this program do, they macroscopically track you electrons, taking into account all the probability of collisions and giving you the precise results. So if you really want a precise results, in this case, you cannot use a formula. You really do a microscopic tracking, which goes piece by piece in doing this. And this is also what is important. So what is important is the speed with which we transfer electrons to the electrodes. This is called the drift velocity, average drift velocity, not which goes random, but average drift velocity with which electrodes drift. A large drift velocity usually obtained by adding to noble gas some of the gas like polyatomic gas. It can be methane, ethane, isobutane, CO2, CF4, which have a large anelectric component at the energies of your electron volt. Remember, excitation energy of argon is approximately 10 electron volt, okay? So in this way, electrons can travel and get continuously cooled down by collisions with these molecules, which actually absorb part of the energy. And large drift velocity is obtained. So you can say there are 3 different candidates, like argon, CO2, which is a slow gases, which gives you drift velocity of the order of 1-2 centimeter per microsecond. You have fast gases. CF4 is the best gas to use as a fast gas, which gives you drift velocity 10 to 15 centimeter per microsecond. And you have the so-called saturated gases, where over the large values of the field, the drift velocity doesn't depend from the electric field. This is important for the drift chamber we will be discussing. These gases is very useful because they remove the necessity to precisely control the electric field and gives you less statistical fluctuation. So we discuss the gas mixture is the addition of noble gas plus some of the hydrocarbons CO2, CO4. But this is not the whole story. This is from the perspective we discussed of the drift velocity, but not only what the drift velocity matters. We need also gases like CO2 hydrocarbons as a quencher in the mixture. So from one point of view, they allow to make a gas faster by taking out the energy from the electron accelerated of the fields. But from the other point of view, there is another point. Whenever you create electrons, ionize argon atoms, you can also excite atoms. In order to excite molecules, you need an energy smaller than the energy to ionize. And if you brought an excited argon into excited states, you can de-excite it by the emission of the high energy UV photon. Okay, so basically you excite it and then it goes to the state. But the point is that, for example, the UV photon from argon has a larger energy, 11.6 work function, than, for example, the ionization energy of the copper cathode done is copper. So basically, you create excited atoms, then they de-excite, they produce photons, and if the mixture is transparent from these photons, the photon goes to the cathode and creates you additional electrodes. So basically, at some point, you quickly will start multiply your number of electrons, what you don't want to do this. And the solution for this, you add, again, hydrocarbons or CO2, because these molecules allows you to absorb these photons and later they dissipate energy, not like argon by de-excitation, by emitting photons, but by dissociation in the smaller molecules. So you see, you remove these photons. This is very important also to stop a discharge or spark in the wire chamber. So these gases, CO2 or CH4, can serve two purposes. One of them, they affect your drift velocity. Another point, they removed unnecessary photon activity, which is created during the process of multiplication and during the process of avalanches. So this is why the selection of the mixture is a very complicated thing, you see, so you need to take into account many of these aspects and the elements. So we discuss about the drift velocity, but also diffusion. What does it mean? Because, for example, if the electron is created and under the influence electric field, it would scatter with the different molecules, but you would have, and then it will move to the anode wire, right? But if you imagine here you created many electrons, it would experience a statistical spread, okay? This is what is called diffusion. So the probability of electron somehow to get, so if you create electrons at a point like, then after some distance you would have it. And diffusion is closely related to the drift velocity. This is also sigma x, because if you look on this coefficient, you will see that it's also a function of electric field, E and epsilon electron energy. So you see, diffusion, like a drift velocity, both depends on the average energy of the electrons. And again, cold gases are those who is close to the thermodynamic limit. So for example, where the average energy of electrons, their cool down, is closer to the thermal energy KT. And CH4 has a very large fractional energy loss. As we discussed, it allows effectively cool electrons. So whenever you add it, you have a lower energy of electrons, lower diffusion. And argon doesn't have energy before excitation and ionization, yeah? So energy continuously increases in this mixture and it has a large diffusion. So basically with argon, you also can do the large diffusion. And here you can see another important question, which is actually discussed, but what is important? Whenever the electron drifts, an electron cloud drift, you have a two diffusion. One of them longitudinal diffusion and another transverse diffusion. You understand? The electrons can spread when they move, both in the direction they move and both in the orthogonal direction. So you have two coefficients which you measure, and which is important depending from the application of gaseous detector you do. And here you can see the diffusions, which is different for different fields and for the different gas mixtures. Sigma L, it's a longitudinal diffusion. Sigma T is a transverse diffusion. And here I would stop for a second. I confused you enough with questions. Was it clear? Yes. Sure.
Okay, in drift velocity curve that with electric field, drift velocity with electric field curve that you have
Yes.
shown, the CH4 curve is dropping. It's not getting in. Yeah, the CH4 curve is not getting saturated. It's because the reason is like I want to clarify it. With increasing electron energy, the cross section for vibrational and rotational transitions, it gets increased. Is it the reason?
No, because I mean, it depends from the cross section of absorption, because with increasing energy, electron needs a smaller distance to gain more energy.
Okay.
And then it comes everything from the cross section. It's less effectively loses an energy. And this is why the drift velocity dropping.
Okay.
So you see, it's very much dependent because electron starts to ionize when they reach 10, 15 electron volt. All the transition of energy collisional they have in the 1 electron volt and 5 electron volt. This is a very important point. And if the field becomes very high, then it quickly accelerates between these two collisions above this 5 electron volt, and then he becomes available for ionization.
Thank you.
Okay. Okay, I know it was a yes. Go ahead.
So, why is there a specific ratio 70-30? Do you know the reason for this?
Why?
A specific ratio like 70 to 30 of.
No, it's a just example. You need some percentage of the quencher and the gas which slows down the electron, and then you select based on your application. It can be 90-10, 80-20, 50-50. So you select by modeling your diffusion and drift velocity with your geometry with Mach-Boltz's program. It was just an example. You can select pretty much any as soon as the amount of quencher is 10-20% with noble gas, it works. By the way, why do we use as a main component noble gas in the gas detectors? Who knows? Why? Why? I was saying always argon 70-30, 80-20. Why noble gas? Why not to use only CO2 or CH4?
Noble gas doesn't deteriorate. They don't change the. Noble gas don't react chemically. The element don't change when electron collide with them. MCS, multiple Coulomb scattering. They don't change.
Okay.
So my question is, what about photons? Do they leave tracks in gaseous detectors?
Sorry, it's
What about photons? Can they leave tracks in gaseous detectors?
protons.
Photons.
Yeah.
So what about photons? Do they leave tracks in gaseous detectors?
No.
Okay.
They can only ionize copper cathode and then create electrons only in this way. And this is what we try to avoid. Photons, no, they don't lose by d over dx. Okay, before I finish, I just would like, I'm finishing. Before I finish, I would like to give you a few things which is very important in principle concerning as we discussed already. I know it was a little bit heavy, but we discussed the electron drift present of electric field. But as you remember, in the time projection chamber, you usually do both electric field and magnetic field simultaneously. So you also need to have a configuration where you drift your electrons in the presence of electric and magnetic field. And this is what you can do, basically make a calculation of assumption. And what is important, it's just a standard presence drift of electron field with the assumption, and then you arrive to the formula, which basically depends from the direction of electric and magnetic field. And what is important, when electric and magnetic field is parallel, like in time projection chamber along the axis, then you actually can significantly decrease the transverse diffusion. So in the transverse direction, this is what is exploited in TPC principle. So basically the diffusion can be modified by the presence of magnetic field, which comes as a part of omega tau. Yeah, you know, you should know this from electrodynamics. So basically it allows you, this is a sigma transverse diffusion as a function of Tesla for one of the gas mixture, where you can decrease by factor of 5 the transverse diffusion. And if you really decrease the transverse diffusion, you increase the precision measurement of your coordinates, okay? So with the use of magnetic and electric field in such a devices like time projection chamber, you can significantly decrease the things. And last but not least, what is important, we discussed, we put your electrons towards the anode, and we want them to multiply at the anode, but some of them can be lost. Why? Because there is another process which is called electron attachment. Some of the electrons, while being in transport, can be attached to some of the molecules which has a electronegativity affinity, yeah? So for example, what is known is the oxygen, CF4, some other gases like CS2, but oxygen is the most dangerous, especially in a big volume. Again, the cross-section and probability of attachment energy dependent. As we discussed, drift velocity energy dependent, diffusion energy dependent, attachment is energy dependent. This is why you cannot calculate it precisely. But for example, oxygen and CO2 can attach electrons. So basically electron goes and then creates CO2 minus ion. Yeah, and you lose this electron which you needed. But this is all energy dependent, and this attachment cross section, this can be, everything is calculated. And what is also important, that usually this is three body processes. It's not like electron collides with a CO2. Electron needs a three molecules, collision with three molecules simultaneously to do this. For example, the addition of the CO2, here you can see number of electrons you lose in the argon CO2 fraction and mixture and argon CH4 mixture. And you see for the same amount of the oxygen, you have a completely different attachment in these two mixtures. That demonstrates you the three body nature of these processes. This is calculated. This is actually why you need, simulation and results. Okay, so I think now time for questions. I'm done. So you have some questions, please come up with more. It was technical, but I hope something remained in your mind, cross sections, some other things. Yes.
I'm saying it has to be some technical.
Yes.
What about the advantages of
everything, they're very advantages. No, I mean, the key points, which is clearly what is Daniel was also showing, and we will be discussing this. It's a radiation hardness, because the admixture of the quenchers, as we discussed, it leads the so-called via aging effect or decreased radiation hardness. Because this molecule, you now know, they absorb photon, they decompose, but the elements from this decomposition can land up on your electrodes and modify your electric fields. And this is what can lead to the degradation of performance characteristics. And this is extremely complicated process because, as we discussed, everything here is this cross-section oriented. So this is one of the points which is there. Then, of course, I mean, the silicon has a major boost now because of the micro, how to say, silicon chips technology, everything. And this is boosts a lot of the developments because we are not using in particle physics the most modern technology with these nanometers, etc. Gaseous detector, they're not so advanced in industry because of the complication. So I think if there would be industry who would boost in this would also benefit a lot. But again, I mean, in terms of, as we discussed, in terms of the precision, gaseous detector cannot aim for the special resolution 10 micron. But if you need to cover large area with a resolution 50 microns with the new micropattern gas detectors, this is where we are, apart from the aging effect. So it finds its own
affects
We will discuss this. This is not, this is black magic. This is, I will not tell you. The agent effects in gaseous detectors, this is pure black magic.
Yeah, I think last question.
For your nice presentation. My question is gaseous detector are applicable for photon, neutron and heavy ion also?
For photon?
Photon, neutrons and
Sure.
heavy ion.
Yeah.
What about heavy ion?
No, I mean, it depends what is exactly. Neutrons, yes. You put, for example, the boron layer within the gaseous detector. Now with helium, you cannot use helium of the price, but you put boron, for example, deposit on surface of detector where you convert new. Gaseous detector can detect you charged particles. You need first to convert neutron to charged particles, either with boron layer, or for example, with the interaction with some of the material or gas atoms. This is like this one. Photon detector, yes, you also can do this, but you need to deposit, for example, photocathode, cesium iodide photocathode on the surface, which is done. You convert photon to electron and you register gas. Gaseous detector can register charged particles. But then you can, in a smart way, convert them and then you register. Yes.
So what is the significance of this delta electron?
Sorry?
What is the significance of this delta electron?
Significance?
And do they play a role in any physics or this delta electron?
Well, they dilute your precision with the measurement of the coordinate. But this you can avoid because you usually have many electrons. The problem is when you do d over dx measurement, energy loss measurement. In this case, you introduce a so-called concept truncated mean, where, for example, you don't count in your d over dx distribution the 10–15% of the largest energy depositions, because this is most probably electron. You would have a Landau tail, okay? Energy loss distribution. And for this, you basically try to remove the delta electrons because they degrade your d over dx resolution.
Okay, I think on that point, thanks, Maksym, for his excellent talk. And we will hear tomorrow more. Just only one point in the experiment point of view, I'm saying, even though you are talking about that measuring this energy of the particle GeV, TeV, but what are the exactly physics? To get this physics, you have to look for EV energy or KV energy, MeV energy. You know that physics. Then only you know how the detector is working, how we'll get these signals. Yeah. Okay. So now in the non-academic part, a little bit of logistics. Just one clarification again, I'm saying we have 16 experiments, but there was some of the experiment is tell 1, 2, or 3. Let's present FPGA 1, 2, 3, all are the same experiment, only 3 group will do separately. So this 1, 2 does not mean that category 1, category 2, this is exactly the same experiment. And so these are just after now we'll have a lunch. After the lunch, the same place where you have the tea, you come here in this, just in front of this building, in front of this room, and respective instructor will take you in your experimental area. And this will start 2 to 4, 6, and in between 3:30 to 4:15, we will have a tea arrangement in the same place where you had the morning tea. So you come in between and have a tea and then go back for the experiment. And then I think I send you a mail. Many of you have seen. It is too early, but today at around 6:15, I want to see it with you here. If you have any feedback, with your feedback, if you feel something we could improve your academic or this non-academic part, something you can improve, just I want to get your feedback. Mainly the feedback when you go for the experiment, including all those. That we will try to the next day to improve it. And today and every day you will have a dinner here. Today dinner will be the welcome dinner. It will be outside the lawn. It will be this at 7 o'clock. It will start, and after that your bus will go for here to this your guest house, and I think bus schedule is already given. Yeah. So that's the things, and this will be the more or less the trend every day, next 2 weeks, 3 lectures, then gap and the experiment and the dinner, and you have to go back. And maybe I will again take another feedback session from you sometimes in between. Okay? Okay, then have a good lunch. By the time it is our next speaker,